So in this video, we're going to be applying the concept of power specifically to electrical power. So in general, power is the rate at which energy is being used or generated. The symbol for power is capital P, and the units, it's a rate of change of energy with time. So it's joules, unit of energy, divided by seconds. Or we simplify that to just capital W, which stands for watts. So that's watts there. If you've ever been shopping for a light bulb, you'll notice that incandescent bulbs, so that's sort of traditional old-fashioned light bulbs, will always say a wattage on them. They'll say a 60-watt bulb or a 100-watt bulb, and newer LED bulbs will often say equivalent to a 60-watt bulb or equivalent to an 100-watt bulb. That's because the power, or the watts, of your bulb tells you how bright it is, which is something you care about for light bulbs. So power tells you the brightness of a traditional bulb. All right, so let's drive an equation for power. So in general, we know that any kind of power, electrical power or any sort of power, is a change in energy over a change in time. But we're specifically interested here in electrical power. So that means I should really look at the change in electrical energy with time to get the electrical power. If you remember the equation for electrical energy, it's delta E is Q times the change in potential. So let's sneak that equation in there. And I'll get power is Q delta V over delta T. All right, but then we look a little closer and we can remember that Q delta T, this little bit right here, is something familiar. That's actually the current. Current is charge over time. The Q over delta T there is the current. So we can replace that piece too. So I'll have power is equal to, instead of Q over delta T, it'll be current times the potential, change in potential, delta V. And that is one nice equation for power in terms of current and voltage. So let's say you had a light bulb and you wanted to know the power through that bulb, or the watts, how bright it's going to be. You could just take the current through that bulb and multiply by the change in potential over that bulb, and you would know its power, or how bright it is. Sometimes though, maybe we don't have the voltage through a bulb and all we know is maybe the current and the resistance of the bulb. So in that case, it'd be helpful to have an equation for power in terms of just I and R only. So we'll start where we left off. So with P is I delta V. But if you remember, we also have an equation for delta V, right? So delta V is I times R. So I could sneak this equation in for the delta V here, and I would get power is I times, instead of delta V, it would be IR. And then let's simplify that a little bit. I have an I times an I, so that makes an I squared. So current squared times the resistance. And that is another handy equation for power. That's really useful if all you know is current and resistance. You can still find the power of a light bulb or whatever device you're using. And lastly, let's say you don't know the current, but you do know the potential, the voltage, and you know the resistance. Then we could get an equation for power this way too. So we'll start with I delta V. We're going to say we don't know the current, we just know potential and resistance. So let's use that same equation, our equation delta V is I times R, but we'll just rearrange this time for current. So divide both sides by R, and I get I is delta V over R. Let's take that equation and plug it in here for the current so we can kind of get rid of the current. So I'll have power is, instead of I, it'll be delta V over R, and that's times delta V. So that gives me delta V times delta V on top, which is delta V squared, and then divided by the resistance on the bottom. So that's a third equation for electrical power. If you know the potential through a light bulb or whatever your device is, and the resistance of that device, then you can just do potential squared divided by R, it's a squared there, and that'll give you the power. All right, let's try using that. So you have a toaster that has 1.2 times 10 to the 3 watts of power, and it's plugged into the wall, so 120 volts. We want to know the resistance of the toaster. So first let's write down our given here. We know the power is 1.2 times 10 to the 3 watts. And we know the potential or the voltage is 120 volts. And the required is the resistance. That's what we're trying to find. So it kind of makes sense to use the equation we actually just derived, that power is the change in potential squared divided by the resistance. To rearrange this for R, you could use your little triangle, or you could multiply both sides by R. That clears the R off the bottom, and then I get R times P is equal to delta V squared. So you could divide both sides by power. That cancels out the power here, and we get a nice equation for resistance. It's just delta V squared over P. All right, let's plug in our numbers. So delta V is 120, so that'll be squared divided by the power is 1.2 times 10 to the 3. And tossing that all into your calculator, 120 squared divided by 1.2 times 10 to the 3. That gives me 12. And the units of resistance are ohms. Let's just check our sig figs. There's 2 sig figs here, 3 there, so our answer should have 2 significant figures, and it does, so 12 ohms is good. All right, a little bit of a more involved example. Let's say you have a light bulb that's made of a coil of wire, and that coil of wire has a length of 2 centimeters. So let's write down our given here. So the length is 2 centimeters, and right away I'm going to want to convert that to meters, so 0.02 meters for the length. The radius of that wire, so R, is 0.12 millimeters. Right away I'm going to want to convert that to meters too, so that's going to be 0.00012 millimeters. The power in that bulb is 60 watts, so it's a 60 watt bulb, and I know the current is 0.5 amps. And what I'm trying to find is the resistivity. So if you remember, the symbol for resistivity is rho. It's a Greek letter. It's like a curly kind of P without the top stick piece. So that's a rho for resistivity. That's what I'm trying to find. All right, this looks kind of messy, but let's start with just a simple power equation and see where we can kind of go from there. It looks like we have a fair bit of information about resistance R, and also some information about current and some information about power. So maybe a good equation to start with would be this one. The power is I squared times R equation. The thing is, I don't actually know the resistance here. I know lots of information that would give me the resistance, like the length of the wire, the radius, and I'm looking for the resistivity. So maybe I'll plug in the equation for resistance of a wire, which is the resistivity multiplied by the length divided by the cross-sectional area. We also know an equation for the area. If it's a wire looks kind of like this, right? It's just a cylinder. So the cross-sectional area is a circle. So that area is just going to be the equation of a circle. So pi little r squared. So little r stands for radius, capital R stands for resistance. So that tweaks my equation for resistance a little bit here. My equation for resistance becomes rho L, so resistivity times length, divided by pi r squared. Okay, let's take that whole equation for resistance and actually plug it into our power equation. So our power equation is going to become I squared times the resistance, which is rho L divided by pi r squared. This looks perfect. I know power, I know current, I know length, I know pi, of course, and radius. All I don't know is resistivity, so I can rearrange this guy. So first let's get the pi r squared off the bottom, so we can multiply both sides by pi r squared. And that gives me, so those are gone now. So that gives me power times pi r squared on that side. And that gives me I squared times rho times L over here. Then next, I want to get rid of everything that's being multiplied by the rho. So I squared is being multiplied by the rho, so we'll divide both sides by that. That cancels the I squared. And also L is being multiplied by rho, the length. So we'll divide both sides by length as well. So that cancels the length too. All right, that gives me a lovely equation for rho, the resistivity, which is, that resistivity is going to be power times pi r squared divided by I squared times L. Let's plug all of our numbers in here. So power is 60 watts. Then we've got pi. Then we have the radius squared, so 0.00012 squared, divided by the current squared, 0.5 squared, and the length, 0.02. All right, toss that all into your calculator here. So 60 times pi times 0.00012 squared divided by 0.5 squared, and also divided by the 0.02. And I get a resistivity of 5.4 times 10 to the negative 4. It looks like I have two sig figs, so I'll keep that. So 5.4 times 10 to the negative 4. And my units of resistivity, if I'm not sure, I can always go back to my original equation for resistance. Let's just rearrange that equation for resistivity. So if resistance is rho L over A, just if you forget your units, which happens to me all the time, rearranging this for resistivity, I would have multiply both sides by A, divide both sides by L. That gives me resistivity is A, the units of area are meters squared, times resistance, units of that are ohms, divided by L, units of that are meters. So if you see what happens here, there's meters squared over meters, so the squared will cancel 1 meter, and you get units of ohm meters. So if you forget your units of resistivity, you can just use the equation to get it. They'll be units of ohm meters. And that is my final answer.